make sure that this is the low temperature deformation process. After that, how the deformation been taking place in titanium, how the fragmentation things occurred, and we can correlate that the deformation and fragmentation behavior by the microstructural point of view. And from there, we have understood that there is a different shear band forms in the titanium that lead to the deformations and the crystallizations that I will discuss. And in addition to that, I will be talking about the deformation mechanism of aluminum, because this is very, very important in terms of welding perspective, or what I can say in terms of whether the tool will fail or not. And it's also important for the mechanical point of view, mechanical property of the weld we are going to develop. So this is the common phenomena we have seen, that is the two body interactions we've seen in case of friction. Friction is nothing but a force between two surfaces that are sliding, okay, or trying to slide during the process. For example, when you try to push a book along a floor, then the friction make this difficult. Friction always work in the direction opposite to the direction in which the object is moving or object is trying to move. Like in this case, you can see here. Here you can see here that this is the surface is try to move on top of one another. This is the type. This phenomena can be seen in a different industry and different systems, like bearing, gear drive, machining, tire on the road, hip joint. When there is a movement between two surfaces. And only thing that during the surface, during the relative motion, there is a deformation at the interface, and that lead to the increase in the temperature and the welding being taking place, micro welding being taking place. And all it finally affect the friction and wear behavior at the interface. And the deformation behavior, what I am talking about at the surface and subsurface level, and it depends on the different process parameter, like what are the load, and what are the velocity, temperature, and the duration of all load applications. So now I'm moving to the friction stir welding. Just you see the how the friction stir welding means, what is that means, then you can easily visualize. If you want to see the friction stir welding, this is a schematic view. I have taken a schematic view. You can see this is the tool being rotated, and it consists of a solder and the probe. You can see here in the tool being rotated, and you can see that when the probe inserted into the abutting interface, that probe actually been inserted into the material, but not the solder. Solder has actually touched the surface. When solder touch the surface, then you are not plunging further. Okay. So after that, what we are doing? We have started the traversing the tool along the interfaces. Okay, and because of the frictions generated between the tool and the material, there is an increase in the temperatures because there is a friction generated temperatures evolutions. And you can see here that there is a two material, one is material 1 and one is material 2. So depending on the deformation behavior of the each material, the actual shear stress developed on the material varies. Okay, by simple terminology. So if the temperature is very low, then what will happen? It is difficult. Tool material, what is been there, it is subjected to wear and tear. Okay. So therefore, sorry. And here there's a few terminologies very important. You can I will be talking at there's a welding directions, the direction of the weld, and this is the transverse direction across the cross section of the weld, and this is the normal direction. This is the perpendicular to the surface of the weld. And this is the aluminum is been placed on the rotating side, and this is titanium is placed on the advancing side. Why it is called rotating and why it is called advancing? Because in this advancing side, you can see the rotation of the tool is in the same direction or the parallel to the direction of the welding direction, and it is in the same directions. It is parallel also, it is the same direction. In case of rotating side, it will be parallel, but this rotation vector and the velocity or the welding direction is opposite to each other. So that's why it is called rotating side. And this is the process zone. Okay, and tool is rotated anti-clockwise. So during the rotation, you can see here, this is direction of rotations. This is the plastic zone developed because of the high temperature being evolved due to the frictions, and this material being plasticized. Okay, and you can see here that because of the rotations, there is a different sort of shear stress developed across the tool. And this any material is subjected to all kind of shear stress. Okay, if it is rotating continuously with the tool. If you think that this is the coefficient of friction is 1 or it is a sticking frictions, then all kind of shear stress, all kind of movement being experienced by the tool. And this is the plasticized material you can see. And if it is close to the sticking friction, that time the tool and the material, deforming material, is try to hold each other. And that is called sticking frictions. And because of that, this is two phenomena could be possible. One is wear out of the tool. If the load bearing capacity of the tool is less or the shear strength of the material is lower than the shear strength of the deforming material or the applied shear stress, then there is a wear out of the tool, and in other case there is a shear deformation of the material. Okay, at low temperature. So these are the two materials very important in case of aerospace industry. That's why we are trying to develop the welding structure for the aerospace industry. And this is a very important material, aluminum and titanium. There is aluminum used 20%. Earlier it was more, but nowadays that composite material is trying to replace the aluminum in the fuselage structure. But challenge, as I have discussed here, the challenge is the difference in the physical property and the formation of intermetallic phase. Because you know, in case of any welding, whenever there is a interactions between two materials at high temperature, there is a diffusion and there is a reaction. Because of that, there is a lowering of the Gibbs energy at the particular composition at the particular temperature, and that leads to the formation of intermetallic phase. And since this is the process, is called solid state deformation process, because whatever the temperature developed, it is a friction based temperature. And you know, friction at the welding, at the melting point is close to 0. As friction, if you just assuming that temperature is increased to the melting point, then friction will reduce, and therefore there is a reduction in the flow stress. Okay, if flow stress reduces, then there is an increase in the coefficient of frictions. So these two phenomena actually counteract each other, and therefore it is a stable temperature development occurs in case of friction stir welding, and that's why we get a very the temperature evolved in this case, in case of friction stir welding or friction stir processing of the same single material is close to the 0.7 or 0.8 or 0.9 of homologous temperature. It's just close to the recrystallization temperature, basically. And in case of welding, friction stir welding, we get two advantages. One is the solid state method, the low temperature deformation process. Therefore, there is a low distortion. And the second case is the three-dimensional mixing. And I was telling there's, you can see here, there's a frictions due to the, there is a crystal structure difference in the physical property and the heat conductivity, and therefore there is a lot of inhomogeneity across the interface. And you can from this diagram, you can see there's a difference in the flow stress of aluminum, titanium. So therefore you can assuming that there's aluminum is not there, but the deformation actually taking place on the titanium. If you nullify the aluminum deformations. So you can, if you just concentrate on the deformation on the titanium, you can see there is a fragmentations, and on this fragment, there is aluminum diffused on the fragment, and therefore there is a reaction. And this reaction lead to the formation of intermetallic phase, because in this zone, there is a temperature is very, very high due to the deformation. Why temperature is very, very high? I will come later. But overall, try to analytically calculate the temperature over here. We can see that we have placed the thermocouple, T thermocouple across the welding lines, and you can see 3 thermocouple is placed. We have get the thermal cycle. From the peak temperature value, we have estimated the degree centigrade. Okay, age of the solder. Why we have taken age of the solder? Because we are assuming that the temperature developed below the solder is uniform. There is two aspects there. And the first or the most important is the recrystallizations, and another is the we can say that the friction value is not overall constant, and we are thinking that it is be close to the sticking friction, and that's why that due to the sticking friction, you can see here that aluminum actually sticking to the plate or plate as well as the tool. And this is the clear information of the sticking friction being very, very active. But at the edge, you can see there is not much sticking. But there is a velocity gradient is very, very high. So the overall temperature, we are assuming that it is more or less constant below the tool solder. And on top of the cross section, this is the cross section image, you can see here that on top of the titanium, there is a coating of aluminum. Okay, so there is interactions between titanium and tool, but this interaction is not constant. And we can say that there is a limited interaction between tool and the titanium. So if titanium will interact with the tool, then we can expect the temperature could be as high as 1000 degrees centigrade. And on that temperature, aluminum basically should melt. But we have not experienced or we have not seen any melting over here. So what is the reason? The reason is there is a limited interaction or the no interaction, and because of the formation of aluminum coating. Because at this temperature at 410, and this is the lower limit actually, that at this level of temperature actually aluminum is recrystallized or aluminum is much plasticized the titanium, and because of the higher plasticity of the aluminum, and it squeeze out of the welding zone and it's form a coating on the surface of the aluminum. Okay, and that's why the whatever the deformation being taken place in titanium, it is a low temperature deformations. Now I'm coming to that what kind of deformation being taken place over here. You can see here, this is the coating developed cross-sectionally, and we have seen also there is a many particles, small particles, and which is mostly more or less from the backscatter image, you can see that this could be the titanium particles. You can see here, but we have also observed this is not fully the titanium particle, where you can see here, this is not fully titanium particles. This is a intercalated particle. What is intercalated means? Intercalated means you can see there is a fragmentation on the inside the particle, and through the fragment, actually the hydrostatic pressure is developed inside the well nugget. This hydrostatic pressure is pushing the aluminum into the fracture location, and therefore it is clutching to each other. The aluminum and the titanium is clutching to each other, and therefore due to the temperature developed during the welding, that at this temperature actually there is some diffusion and reaction been taking place inside the particle, and this form some kind of mechanically mixed particle. Okay. And that is called intercalated particle. It's a thermomechanically developed particle because temperature and the pressure both are involved in developing this sort of particles. But while you are measuring the temperature, we have I was telling that it could be the low temperatures. But how do you sure this is the low temperature? For that, or I have told that the temperature below the solder is uniform. Yes. So to understand the behavior further, we have also developed the friction stir welding modeling, friction stir process modeling using deform 3D. You have seen this is only the processing model. I'm not telling that this is fully justify the model, but one thing is that we can see whether the temperature below the solder is constant or not. Okay, so this is the primary work we have developed. We can see, and we have actually omitted the tool to see or to observe that what kind of temperature, what level of temperature developed. So this is the different material actually, so that's why we are getting little higher temperature. But basically we have seen that the temperature below the tool solder is more or less constant. You can see the variation is maybe 20 to 25 degrees centigrade within the tool solder, below the tool solder. Okay, so you can see. So this is the idea. From there, we have some sort of conclusions that okay, what are the predictions? Okay, that may be correct. Then we have done the tomography of the weld zones, and in this tomography image we can see we are omitting the aluminum. We are only seeing the deformations or the distribution of the titanium particle. So you can see that from microstructural view or macro view, we can see the particle are inhomogeneously distributed. Here also you can see there is no sort of arrangement we can see. Even in the original image, if you see the original image, then also you cannot have a better understanding that how the deformation take place and what kind of distribution have take place. But one thing is that you can understand that throughout the weld nugget, you have some particles. Okay, so the particles are more or less homogeneously distributed, or you can see that in all locations you have some particles. And that is because of the deformations in the titanium side. You can see that at the top side you have a higher deformation in comparison to bottom because of the solder affected region. Then we have seen at the different locations, we can see this is the retreating side, this is the advancing side, and this is the top, and this is figure out the distribution. And one thing, even though they are more or less haphazard, but one thing we have seen that the deformation behavior or the fragmentation behavior of the titanium has some similarity. What is the similarity? That if you reduce the particle size, okay, that when the particle size reduces continuously at each location, there is a increased fractions of the particle or increased number of counts of the particles, or other words, the particle size, the very fine particle in each locations are having the more numbers compared to the particle compared to the particle with cores with higher particle size dimensions. Okay, so this is the observations. Then we have what I can say, we have separated out the particles based on their volume or the particle size, and we have seen that very fine particles are more or less homogeneously distributed compared to the coarse particle. You can see there is a lot of whites, okay, and their distribution, their orientations is not very homogeneous. But you can see here the fine particles are having the very good distributions. Okay, so this is the one thing, and this is the other things. Okay, from there there is a possibility that particle might be therefore the coarse particle which is developed initially could be subjected to fragmentation further, and that's why it will lead to the formation of smaller particle or the finer particle, and therefore we can expect that finer particles counts has increased in each locations, and we have seen the very same things over here. And similar approach we can see over here also. So fine particle fractions is very, very high, or the number of particles, number of finite particles is very, very high compared to the coarse particles. And when we have seen the microstructure at the interface, this is the interface, this is the aluminum side, and this is the titanium side. And we have also seen that there is a recrystallization in the titanium. So this is quite unusual phenomena in case of titanium, which is subjected to deformation at low temperature as low as 410 degrees centigrade. At this temperature, we generally do not expect the recrystallization being taking place. Okay, this is the recrystallized phenomena. You can see it's a different grain orientations, and this is the mostly high angle grain boundary. You can see this is the 15 to 180 degrees deviation. We can see this is the high angle grain boundary. And from the CAM map, this is the CAM map. From the CAM map, we can see this is actually it shows how the dislocation been distribution is more or less homogeneous. And even from the Gauss map, which actually define the define the recrystallized grains, where is that blue, and the orientation deviation from 0 to 2 actually called the recrystallized grain. From there we can see there is a recrystallization grain. There's a huge number of recrystallized grain is been present over here. So this is sort of recrystallization being taken place. So this is quite unusual phenomenon in case of titanium, which is subjected to high standard deformations at low temperatures. Then you have try to understand how the deformation been taken place. So to understand that, we have started the microstructure from the base metal towards moving from base metal to the interface. We have already seen the microstructure of the interface. Then we have seen the microstructure and at the base metal. You can see this is figure 4. Similar sort of thing what we have seen in the interface, but only thing that grain structure is very, very high. Here the grain structure is close to more than 50 microns. Okay. As we are moving close to the interface, we can see there is a huge fraction of twinning, and the microstructure also somehow refines compared to what we have seen in the base metal. So from there we can understood that since titanium have HCP crystal structure, which is having only three slip system, where 2 independent slip system, and titanium has a low thermal conductivity. Okay. the deformation leads to the temperature evolution, that could not transfer from the metal or the deforming locations to the surrounding locations and high standard deformation conditions. And titanium could not accommodate large amount of strain as well. So therefore, as we are moving from this metal to the interface, we can see there is an increase, there is a possibility or not possibility, there is certainly that the increase in the strain, okay, and the strain rate. So you can see that due to the increase in the strain, there is a formation of twins because titanium is having lower number of slip systems. So twin is the second, another mode of deformation, okay. And at the interface, we can see there is a possibility of formation of adiabatic shear band, and this lead to the formation of each formation. There is evolution of the higher temperature close to 700 to 1000 degrees centigrade, and that could possibly lead to recrystallization in titanium at the interface, okay. But if the recrystallization been taking place due to the adiabatic shear band process, then we can expect the similar features in particles as well, because this is the adiabatic shear deformation process. That means the shear deformation been taking place only at a certain locations, not in the gross level, okay. So that adiabatic shear band also promote the formation of voids, and when during the deformation these voids actually connected to each other, there is a possibility of formations of particles. The same thing we can see here, there is a formation of voids, we can see, and when it is connected, it's formation of crack. And during the deformation, that crack developed further along the deformation at the shear deformation directions, and that led to the formation of particles. You can see that this is the particle is actually formed from these locations, okay. And similarly, this is the another location you can see. This actually the shear band deformation, shear band driven fractures. Otherwise, there could have a gross deformations or elongations further. Here you can see there is a crack is developed inside the particle, and that lead to the formation of particle. You can see there is a fragmentations, and from the geometry you can see that this is the particle. This is the particle which is actually developing from the original particles. And this is the another sort of example from the geometry. You can see two particle geometry, that this particle actually forming or separating out from the original particles, okay. So this is the method, or this is the mechanisms, okay. As I already discussed, this is the mechanism which lead to the formation of particles as well as there is a recrystallizations. And this is the recrystallization phenomena, as I already discussed. When there is a very fine particles, there is a higher surface to volume ratio, or it lead to the higher surface reactions, leading to the formation of intermetallics as well. So there's a very fine particle which is not actually the titanium particles. It's actually subjected to reaction and lead to the formation of intermetallics. There are some examples where people have also observed that this is the adiabatic shear band. On the adiabatic shear band, people have observed the recrystallization grains. You can see there's a very fine recrystallized grain, and this is the deformation grains, okay, but it's not subjected to recrystallization because it is adiabatic deformation process, and it is the EG flow directions, EG flow locations, or the flow, what is called flow stress in the adiabatic shear band is very, very low, and therefore will lead to the fracture, lead to the higher amount of shear deformations. And this is the quite bright field image of the EPS fine grain. You can see core of the shear bands, and there is no dislocation, there is no twinning. So this is clear evidence of adiabatic shear band driven recrystallizations, what we have seen in our experiment as well. And there is the few examples from the microstructural point of view. You can see from the optical microstructure, we have seen there is adiabatic shear band formations, and this adiabatic shear bands is parallel to each other, and it's acting along the shear directions. Because at the advanced side, the deformation direction is from the bottom, or the flow of the material direction is from the bottom to the top because of the hydrostatic pressures and because of the shear rotations as well. So we can see there is a deformation direction. We can see there is a mark of the adiabatic shear band line. From the tomography image, this is the shear direction. You can see there is a crack developed in the particle, and there is a separations. There is a fragmentation of the particle leading to the finer particles, and this is the mechanism. In the advancing site, where the titanium is present, actually lead to the formation of adiabatic shear bands, and this adiabatic shear band lead to the formation of particle, as well as at the interface due to the high shear deformation, there is adiabatic shear band driven recrystallizations also we have seen. In the aluminum side, we have seen very good, well recognized recrystallization microstructure. From here, we can see there is a few grains. We have already marked this grain boundary. There is a three type of grain boundary being possible. If historically, this is low angle, sub-angle grain boundary. This is low angle grain boundary. This is high angle grain boundary. Any grain is surrounded by only the high angle grain boundary. We can call it a grains. Okay, complete grains. Okay, here you can see there is no complete grain as such. Okay, there is a development of the grain, and during the development process or during the formation of the grains, there is a development from the sub grain to the low angle to the high angle grain boundary. You can see here. Okay, sorry. You can see now, I guess. Shekharji, can you see now?
It's visible, sir. It's visible.
Okay, okay. So you can see there is a increase in the grain boundary from the low to the higher grain boundary, and this is the process by which the grains has formed, and this is because of, you can see few grains, low angle, then sub grain, then low angle grain boundary, then lead to the high angle grain boundary. So this is the typical features of continuous dynamic recrystallization phenomena. And since the aluminum has having higher number of slip system and higher stacking full energy, so this is a common phenomena that recovery recrystallization based microstructural evolutions. And we can see from the Gauss map where the 0 to 2 degree orientation, I told the grains having that within these orientations, deviations, that actually represent the dynamic recrystallized grain, and where from this micrograph you can see the 78% grain are dynamically recrystallized. So the aluminum side is totally recrystallized and it has a lower flow stress, but on the titanium side we have a strong material like titanium which has not been recrystallized, which is subjected to the low temperature deformations. So this is clear evidence of such that, and from this microstructure, also we can see the Gauss map of with different grain size. We can see the bigger grains actually subjected to deformation. This is not a low value of Gauss, but this very finer grain, we can see there is a very low value of Gauss. Okay, so that actually represent, in case of aluminum, that the bigger grain is subjected to deformation leading to the finer grain, or it's a process of refinement, grain refinement in case of aluminum. So this is the common phenomena in case of welding. So it does not have much relevance in case of typology, but one thing is that what I'm showing that different kind of intercalated structure that actually, and there's a matrix is very ductile because it's consists of aluminum, which is very much recrystallized, and this is the particle. So because of this particle distribution, you can see there is a scattered in the hardness values. And this scatter is not homogeneous, this is heterogeneous because it depends on the particle distributions as well. And we have observed a very good mechanical property. You can see very good ductility, as well as we can see that the fracture location is away from the zone because of the particle distributions. And we have observed very good fatigue property as well. So this is the typical phenomena we have generally observed in case of welding. And this is the fractograph. It shows that fracture surface is composed of some particles, as well as the fracture surface does not have particles. So it is a transition zone actually lead to the fractures, that thermomechanically affected zones and the basement or weld nugget, that is the interface actually leading to the fractures. And this some sort of brittle fracture you can see here, some sort of ductile dimples also you have seen. So this is the different mechanisms at the different location leading to the fracture of the tensile sample. So in the whatever we discussed now, we have seen that this is the continuous deformation mode actually leading to the finite particles, and we have also seen that finite particle actually lead to the higher mechanical property of the weld. So therefore, we have done to continuous welding or the multipass welding or the multipass processing, we can say in your terminology. So then we can generate more number of finite particles. So that we have seen here. So as you have done the second pass on top of the first pass, we can see very higher fractions of finite particles. And that actually distribute in the weld nugget, and depending on the microstructure, we can see there is a very fine intercalated structure, and there is a very thick layer of intercalated structure, and there is a higher fraction of deformation. From here you can see in the weld nugget. Based on the microstructure, we have correlated the microstructure to the spring model, because in this case you can see in this location at the interface you have intercalated as well as the intermetallic layer. So these two actually connected parallelly, but other different zone actually connected perpendicular or series. So similarly, we have expressed or we have developed a model, and we have seen that this model actually correlates very well to the stress strain behavior of the materials. So this is the summary of my presentation. So actually what we have learned from here. So this is the low temperature deformation behavior of the titanium we have seen. And from the welding perspective also, from the tribology perspective also, we have seen the deformation, how the deformation take place in different cases, like in case of two-body abrasions and other things. So it's actually the tool and the titanium actually subjected to shear deformations at a low temperature, and that led to the fragmentation and the dynamic recrystallization, and the mechanism which is involved or which is leading to such microstructural development and is adiabatic shear band formation. And why is titanium subjected to adiabatic shear band? Because of it is having lower number of slip system, lower thermal conductivity, and that lead to the adiabatic shear band formations. And because of the adiabatic shear band formation, we get different kind of finer particles, and this particle fractions is very important, because if you deform the material further, we can get very finer particles. Okay, and this is a continuous process, and because of that, we can tailor the microstructure in the weld nugget in case of welding, and we get a very good mechanical property of the defect-free welds. So this is the end of my presentations, and I always believe that every ending is just a new beginning. So I hope this is our collaborations, or this is our discussion, this is our friendships. Thank you for your kind attentions. If you have any questions, I'm ready to discuss.
Thank you, sir. Thank you very much. That was a wonderful presentation. Let's see if anyone, like any of the participants, with their queries or something. If we don't have any queries on the question and answer.
Okay.
Participants, I request if anyone have the doubts or queries, you can post on Q&A, or you can straight away ask Professor. Or still, if you don't find time for the questions and all, you may just post your questions on group so that we can forward to Amlan sir, and we'll come back to you with the answers and justifications. It seems one is TCH Anil Kumar. Sir, here is a question from CH Anil Kumar. Are these type of studies for any other tool materials?
What is the question?
Something seems to be. I'll do one thing. I'll connect Mr. CH Anil Kumar sir, so that he can straight away speak to you.
Yeah, I can answer that.
He's like recording. Like Anil Kumar sir, are you there, sir? Hello, Anil Kumar sir.
Sir.
You may speak to. Yeah, it's audible, sir.
Yeah, sir. So good afternoon, sir. Sir.
Good afternoon.
Sir, that's a very nice brief presentation, sir, regarding the friction stir welding. Sir, regarding the friction stir welding, apart from aluminum alloys and the titanium tool you have used, for any other type, what is there any dependence on the tool orientation angle during friction stir processing?
How do you mean by tool orientation?
Suppose, sir, generally the tool which will be blend, that it will be made vertical to the surface during friction state. Suppose if I bend the tool like some 0 to 5 degrees, if I vary the orientation of the tool, there will be any change in the effect?
Then other kind of orientation is not possible, because otherwise we will not get the you will not get the volumetric deformations. Yes or no? So your tool should plunge into the material, and then only there is a possibility of deformations, or there is a shear deformation, whatever I was talking.
Sir, is the tool tip cylindrical or trapezoidal, sir?
No, you can make anything. So people have defined or designed different tool tip as well as different solder geometry. Okay, there is no boundary, because you need to actually depend on the what kind of what is your expectation. Like people need higher flow in the material.
Yes, sir.
Okay. So in that case, people used to go for different hexagonal cross section as well.
Yeah, because some of the studies
spiral cross section, spiral on the tool, because in the spiral in the tool mean you are actually creating some sort of turbulent flow into material. So if you take a very symmetric or featureless tool or probe, okay, what will happen? You are actually developing very homogeneous flow.
Okay.
So it's depend on what is your intention. I don't want any sort of turbulence, because you can see there's tool and the solder interacting each other in the low temperatures. Okay. In case of titanium.
Okay.
If you take some sort of what I can say spiral, what will happen? The edge of the spiral is subjected to high amount of stress.
Yes.
And that led to the failure of the features itself during the process. Okay. So we can do actually. We can do it only depend on the sustainability of your tool, whether your tool could sustain that sort of shear load or not.
Okay.
Okay. If you just take very high strength material like tungsten, rhodium, and other stuff like that, then you can do easily.
Okay.
Okay, that's why in the beginning itself, there is a two possibility. You can deform the material, otherwise there is a wear out of the tool. And
Sir,
many people have studied wear out of the tool, how the wearing been taking place. Okay,
yeah.
that sort of studies are also there.
Sir, in some of the papers, they are accompanying this process with the ultrasonic vibrations.
Yes.
Does it have any other impact better than this? The improvisation of properties.
Yeah, because that is the physics point of view. If you give the ultrasonic vibration, the atomic vibration they are taking into considerations during the deformations in the high temperature. You know, at high temperature, material will vibrate.
Okay.
The atom will vibrate from its original positions.
Okay. Thank you very much.
So because of that, there is an internal energy developed inside the material. Like many people have collaborating friction steel with different sort of welding method as well, like laser welding.
Okay, okay.
That is actually the heating the material.
Yes.
Okay, like you know that microwave, the similar sort of thing. You do ultrasonic or the microwave vibration sort of things.
Yeah, because this excitation of energy due to ultrasonic, it may also benefit us in giving the input energy while friction steering.
Yeah, that is the same thing. Like ultimately, your objective is to plasticize the material during the deformations.
Okay.
So to achieve that, people use different methods. Some people heat the material in a different way. So ultrasonic is also another way of excite the material or excite the material to have a easy plasticity.
Okay. Actually, I'm looking over into this area, so that's why I asked out. Maybe my doubts look silly.
It's okay, sir. Anil Kumar, sir. Nothing wrong. So thank you very much, Anil Kumar, sir. And Amlan, sir, thanks for your elaborated explanation and clarifying the doubts of the participants. So seems we have one more question from Professor Radhakrishnan, sir. CMGF or SPD of greater efficiency? I'm not clear with the question. Possible, I'll connect Radhakrishnan, sir. He can speak to you.
Yes, I think severe plastic deformation, you're telling?
CMGF or SPD for a greater efficiency.
Severe plastic deformations. You know, CMGF, what is the full form?
Even I'm not getting. So let's see whether he's there or not. Radhakrishnan, sir, you are there, sir?
Yeah, am I audible this time?
Yes, sir, you're audible, sir. Thank you.
Yeah, see, I am a cardiac surgeon. I am not an engineer. So just correct me if I'm wrong. See, if you are looking into dynamic recovery and activation of, am I audible now?
Yes, sir, you're audible, sir. You may please go on.
See, is it possible to achieve greater efficiency in microstructure fragmentation, like he was telling for plastic deformation at lower temperatures? Would doing cryomechanical grain fragmentation or SPD, which would be a more efficient method?
Cryomechanical
grain? That is plastic deformation, no? Whether plastic deformation or this cryomechanical technique would be better. Cryomechanical grain fragmentation.
CMGF, sir. Cryomechanical grain fragmentation.
I think that SPD is much better way because you are imparting a lot of, you are actually developing a lot of dislocation density.
Yeah, this is okay for nanocrystalline state when you are looking into several tens of nanometers also. Then also you feel that
you cannot develop by SPD that so much nanomaterial so easily, especially for aluminium.
Okay.
Because this is a thermomechanical process. In the thermomechanical process, you know, there is a possibility of grain growth as well.
Okay.
So I think cryo might be a little better because thermal effect will be nullified.
Okay, because I had a feeling that when you go to those nanometer sizes, CMGF may be better.
Yeah, could be, sir. Okay. I don't have detailed understanding on that.
Okay.
but yeah, I feel you are correct.
Okay, thank you so much.
Thank you, sir, Radhakrishnan sir, and
Yeah.
thanks to Amlan sir. So
Thank you.
seems we have no more questions on Q&A. Now it's time to express my sincere gratitude to Dr. Amlan for his wonderful presentation on the topic of low temperature deformation and interface in dissimilar friction stir weld. Thank you so much, sir, for sharing knowledge and for your experience. Hope this talk would help our attendees a lot, those who are working on this low temperature deformation and friction stir welding. To mention that Anil Kumar seems to be working on friction stir welding. So definitely this would give a good information, and this talk would help a lot for people, those who are working on these areas. So once again, I would like to express my heartfelt gratitude to Amlan sir on behalf of Geetham University and management. Thank you so much, sir, for being with us and sharing your knowledge, sir.
As well.
Thank you very much, Amlan. It was a wonderful presentation. I was enjoyed, and then participant also might have enjoyed your lecture. Thank you very much, Amlan.
Your last slide is giving a very good information, sir. Every ending is really just a new beginning. So simply it resembles the cyclic process. From where it starts, it ends. Again,
and
it starts
a positive vibration, sir.
Exactly. And I appreciate my all attendees and participants for having a good active participation and participating in this question and answer session. Professor Radhakrishnan is basically he's a medical, sir, belongs to his non-engineering, but he's very curious to attend almost all our sessions.
Thank you. He has given something new.
Yes.
So
he has been giving all the challenging tasks to almost all the speakers. But one thing we should appreciate that professor, like, is out of curiosity, he used to know more about how this tribology can be maybe utilized in his research areas. Thanks to Radhakrishnan sir, and I appreciate his like a kind of a motivation. Thank you very much, and thanks all panelists, Sandeep, Ashok, and Amlan sir. Thank you all. Thanks one and all. So Amlan sir, we wish that this relationship would be extended, continued for forthcoming events also. We need your knowledge sharing in coming events also. Thank you, sir. Thank you so much, and thanks a lot, sir.
Thank you very much. Thank you very much.
Thank you.
Thank you, Amlanji.
Yeah, bye.
Thank you, sir. Bye-bye. I'll stop sharing.
My camera is not.
Bye,
Thank
sir.
you.
Bye-bye, sir.
Thank you very much.